I'm Connor Higgins.
I'm Mason Mollenhauer.
I'm Tyson Demgen.
And Justin Raffa.
We're here today to introduce the Smart Rover.
The Smart Rover is an autonomous vehicle capable of following a non-linear path while detecting obstacles in its way and acting accordingly. The frame, wheels, and axles of the Smart Rover were designed in SolidWorks and 3D printed. The frame is a box that's open on the bottom that has holes in it to allow easy access of wiring. Additionally, other holes were cut out to cater to different components such as the distance sensor, as well as the motor mounts.
To power the system, we have two power sources. One is an AC adapter, which is used to power the motors. With this board here, we have a display to show the voltage going into the motors and a screw here that the user can change to adjust the voltage going into the motors. We also have a 9-volt, which is used to power the Arduino, and that can be turned on and off with a switch by the user. The main microcontroller for our robot is an Arduino Uno. From there, we have this motor driver chip, which is used to power both the motors. And then for our sensors, we have a LiDAR distance sensor so we can measure our distance, and these infrared sensors to detect the line underneath. And then some outputs we have is our buzzer to make the sound and these LEDs.
The laser sensor works with our outputs, the buzzer and the 3 LEDs, to tell the user if there's an obstacle in its path and to stop the cart accordingly.
So our laser sensor sends out a signal or a laser which bounces off an object and returns, and based on the time that it took to return to the sensor, it'll output a numerical distance value, which will then be sent to the Arduino and then will be used to power the LEDs and the buzzer. Okay, so based on the data received from the sensor, if the data is greater than 250 millimeters, the green light is on, which is our first safety zone. No buzzing means we're good to go. And then as the object moves closer and it comes between 125 millimeters and 250 millimeters, the yellow light turns on, which we call the caution zone, and the beeping beeps every half second. As we move into the danger zone, the red light blinks rapidly and the buzzer beeps constantly.
The two more sensors on the front are these infrared sensors, which are the key component to how this car stays on the track when driving. This is the infrared sensor itself. It features 2 LEDs on the front of it. This one's the emitter and this one is the receiver. They're positioned on the front of the car so that the emitter is always in the middle and the receiver is always on the outside. Now, there's a specific reason for this is because as the car is driving, the emitter is sending a small light signal which the receiver receives in order to drive forward. So as the light bounces off the reflective surface of the table, it is received by the receiver, telling the motors to still go forward. Now, as it goes over the black tape absorbs the signal from the emitter and is not retained by the receiver, giving the motors a different command. We added the casings to these LEDs so that they're only emitting or receiving straight downward, which helps with the accuracy of the infrared sensors. Now, while both these LEDs are on and the light is being received from the emitter in the receiver, these motors are told to drive forward. But as we approach this curve here, we see that it stops receiving the light, the receiver stops receiving the light from the emitter, which tells the Arduino to do 2 things. One, it tells this motor to go in reverse, and it tells this motor to drive forward. So the same side motor drives in reverse, the opposite side motor drives forward. This effectively pivots our vehicle until both lights are solid green again and both sides are receiving the light put out by the emitter, which effectively puts it back on course so that it can drive forward. Here's a demonstration of how the IR sensors interact with the motors and back. Notice the green LEDs as they switch from 2 solid on the reflective surface and switches to only 1 solid when it gets on the absorbent black tape surface, and how it moves through this curve.
So as I activate the user input, you'll notice that the IR sensors are on a totally reflective surface, so it's just constantly going forward. And you'll also notice that the wheels are, or the motors are pulsing instead of going at a constant speed. This is done because the top speed of the car was too great for our sensors to read. So we added a delay to the code in order for the speed of the total car to decrease and give our sensors enough time to read the sensor, or read the line. And continue on.
Alright, so for our demonstration today, we got our cart set up on our track here. Two infrared sensors are currently off the black tape, so it should set in a forward motion once we toggle the user input of the on switch here. We are holding the power cord that goes to the voltage adjuster and back just because it does start to interfere with the pivoting a little bit, but we're going to get it started on the track today. So it starts to pulse forward, and as it goes over the black tape, it reads that it needs to start pivoting back the other direction. And as we approach the first obstacle, the distance sensors are going to start picking up our first obstacle here, meaning it's in the caution zone. As it gets a little bit closer, the red LED starts flashing and our buzzer is constant, meaning that we're too close to an obstacle to keep moving. Once we get this guy out of the way, it should just resume its course. Now we're approaching the second obstacle. We re-enter the caution zone. And now we're in the danger zone. Move this guy out of the way. And it should be able to finish the rest of the course to where it hits the black end of the tape. Now when it hits this black end, both the infrared sensors will be over black tape, so the receivers will not be receiving any light, meaning that this guy is just going to stay in place.